Greetings and welcome. In the last two video sessions, we have seen an expression for shear stress and velocity distribution for a steady and a laminar flow passing through a horizontal circular pipe. In another video session, we have seen an expression for discharge and average velocity of a flow passing through a circular horizontal pipe. Continuation with that, in this video session we are going to see an expression for pressure drop in a horizontal circular pipe. The said equation is called as Hagen-Poiseuille equation. So in order to obtain expression for pressure drop in a circular pipe, we consider from the last video session expression for average velocity in terms of pressure gradient. That is what U average is equal to minus 8 by mu into pressure gradient into radius square. We arrange the term of this equation in order to get pressure drop. That is why we keep delta P, delta P on the left side is equal to remaining terms 8 mu into average velocity divided by radius square into delta x. Then to find the pressure drop in a pipe, we have to integrate this equation. So for that purpose, we use the diagram here. In the diagram, we take the section 1,1 at a distance x1 from the left side and section 2,2 at a distance x2 from the left side. Thus, while integrating the equation, we do integration between the 1 and 2 section. So, writing the integration here of the left side, that is between the limit lower limit 1 to higher limit 2 integration of minus delta P is equal to right side. Integrating this term, we write in the lower limit, that is a location distance x1, and higher limit, that is a location distance x2. Here this term after the integration sign. After that we take this minus sign outside of the integration. Integration with lower limit 1 to 2 delta P. Right side 8 mu average velocity and radius, these three terms are constants, that is why these will be outside of the integration sign. Remaining will be what? Integration x1 to x2 of dx. Now taking the integration of delta P will be what? P. This 8 mu into average velocity by r square, these three terms as it is. Integration of delta x is x. Now putting the limits over the square bracket, lower limit 1, higher limit 2 on the both side. Now while doing the next step, we take higher limit minus lower limit. So here on the left side for the pressure terms, minus sign outside of the bracket, higher limit P2 minus lower limit P1 is equal to 8 mu into average velocity by r square. Inside the bracket, putting the higher limit of distance x2 minus lower limit of the distance x1. Now, with the help of the diagram, we know that this is a x2 location of 2 and x1 location of 1. We need here distance between these two, section 1 and 2. That will be what? Length of a pipe considered for pressure drop. That is why x2 minus x1 is equal to what? L, capital L. Then radius of this pipe is a small r. We need here that to express in the form of diameter. Thus we use radius capital R is equal to d by 2. So substituting L and this radius in the above equation, here we process this minus sign to the inside terms. Thus here we find this minus sign with this minus sign of P1. It becomes plus P1 minus P2. So left side. On the right side of the equation, 8 mu average velocity into, for this we take capital L divided by, here we put d by 2 inside the bracket, square. Doing the square, we find here d square by 4. This 4 will be coming at the numerator in the next step. So that is why 4 into 8 mu into average velocity into length divided by d square. Now this P1 minus P2, this is what a pressure drop taking place in a circular pipe. That is why we use here notation delta P. Right side will be what? 4 into 8 means 32. Remaining terms mu u average L by d square are here. Thus we get this equation for pressure drop in a circular pipe. This equation is known as Hagen-Poiseuille equation. Thus, in this video session, we have obtained equation for pressure drop occurring in a horizontal circular pipe for steady and laminar flow, which is called as Hagen-Poiseuille equation. Let us meet in the next video session. Thank you.